And I would like now to formally start the hearing by calling on the presentation from Bruce Power as outlined in Commission Member Document 15H 2.1B, C, and D. I understand that Mr. Duncan Hawthorne will make the presentation. Mr. Hawthorne, please proceed.
Good evening, Mr. Chairman, members of the Commission. For the record, my name is Duncan Hawthorne. I'm the President and Chief Executive Officer of Bruce Power. Firstly, let me say I greatly appreciate the Commission being here in our community. I think this is a very important part of the whole regulatory process, that people in our community have the chance to see the workings of the Commission. I'm sure as we go through these next few days together, you will see a community that's very engaged in the activities of our site, and a very diverse range of interventions, but on the whole very knowledgeable about our activities. So as I suspected would be the case, a lot of interest in what we do on the site, and the whole process is enriching by that. So we are very happy to see this process run. I also want to thank Chief Root for being here, and part of his words, although I didn't understand them all, as you might expect, I know the great respect with which the Saugeen Ojibwe treat the land, and I'd like to think that we do our very best to meet the expectations and standards that they have, and so I don't. I've always believed that we have a position of mutual respect for each other, and when Chief Cargay was the chief, we talked often about me being a good neighbour, and he said, "You're not a neighbour, you're a tenant." And so I always remember that quote. I say it often, and so any comments I make in the future are with the respect due for the Saugeen Ojibwe's traditional rights. So I thought worth mentioning that in the beginning. As we mentioned, and was mentioned by the Secretary at our Day 1 hearings, we provided very comprehensive information to the Commission staff, so I won't draw the proceedings out other than to say that in our supplemental position we sought to amplify some questions that were asked by the Commission, provide some more material to assist the Commission in its deliberations, and also to flesh out some of the points that are in evidence in some of the interventions. And these are really the supplemental things we want to talk about. Firstly, Mr. Saunders, who the Commission are well aware of, our VP of Regulatory Affairs, will speak to our Fukushima upgrades. Gary Newman, our Senior Vice President and Chief Engineer, will speak to some of the activities related to PSA. I should also say that with us this evening is also Len Cluett, our Executive Vice President and Chief Nuclear Officer. So for the purpose of keeping the Commission hearings on track, I'd like to hand over now to Mr. Saunders to discuss Fukushima upgrades. Thank you.
Good evening, Frank Saunders for the record, and we'll just see whether I can get this presentation up as well as I should. There we go. So as it's been our practice since Fukushima, really starting in 2012, each year we've made a video that kind of documents the progress we've made in installing the equipment and the new material. And what you're about to see tonight is the basis for what that video will be this year. Unfortunately, you get to listen to me stumble through it a little bit rather than quite as slick as it'll be in the video in a month or so. But I think it does a very good job of showing the progress that we've been able to make over the last 3 or 4 years. And it's fairly substantial, again, especially when you consider in our field it takes a little while to make changes because of the rigor with which we do it. So with that, I'll move into this. So the CANDO design and nuclear plants in general designed to be pretty safe. They've got a lot of redundancy and diversity built in their systems, and we'll talk just a little bit about that at the front end.
Well, we use a defense in depth approach to make sure we have adequate safety to the environment and to the public. And what defense in depth means is having highly reliable redundant equipment, highly trained operators, and layers of safety systems to ensure the safety of the public and the workforce here at Bruce Power. 2 independent shutdown systems are poised whenever a reactor is operating. Either of them can shut the reactor down in just seconds if operating parameters are exceeded. likely event of a coolant leak, an emergency cooling injection system is poised to supply water to the reactor to keep the fuel from overheating. Pumps would circulate this water as long as necessary with standby emergency generators providing power if needed. The reactors themselves are enclosed by large concrete vaults that contain heat and radiation. The vaults are connected to a large vacuum building that is designed to relieve pressure and provide additional containment and cooling.
So this is the way that plants have been designed traditionally, and they've been very safe over the years. But Fukushima brought upon a new concept in that, you know, the plants were self-contained. They had many levels of redundancy and backup power and so forth. Fukushima demonstrated that perhaps in some circumstances that a situation could arise which would actually disable all of that because it's all in one place. And the event at Fukushima was a very significant event, not likely to happen on a very high frequency, but still, you know, some level of plausibility. So the challenge then became how to prepare for this type of event, which is of high consequence but very low probability. And in this area, of course, we have a couple of things that do happen on some frequency. You've seen the ice storm, and this is a picture of the Goderich tornado from a few years ago, an F3 type of tornado that was just sort of 50 kilometers south of here. So we looked at an enhanced emergency response approach that would allow us to provide even a broader level of diversity into our protective systems. And we wanted to add some additional layers to defense, primarily aiming at the two things that a nuclear facility needs most of all, which is backup power and cooling water. So emergency makeup water we looked at in a number of different places. And this just illustrates the changes we've been making and what they look like. If you look at the model of the reactor, which I have next, you'll see the reactor itself in the center with the you know, darker color representing the hot fluid from the reactor circulating through the steam generators on top. There in our reactors, of course, there are 4 steam generators on each side, so a total of 8 per unit. And that hot water from the reactor boils the water in the steam generator and produces steam. In normal operating mode, that's the way it works. If you should lose a heat sink through the turbine, then the large relief valves on the top will lift in order to relieve the steam to atmosphere and cool and depressurize the heat transport system. In an emergency situation, this is exactly what you want to happen. You don't require any pumps. The heat transport system will circulate naturally. Cool water up at the top and the reactor at the bottom, and it'll cool, and the fluid will circulate with no pumps and no power. To make this happen, you need a few things to be done, though. Number one, you need the boiler steam valves to be open so that there's somewhere for the water to go, so it steams off as steam. Now, there are different ways you can do this in the plant already. What we did was add another manual way of doing this through independent air tanks so that we're sure that we can open these valves and lock them open. Second thing you need is water in the steam generator. So the first path to water in the steam generators through the inter-unit feed water tie is in place. It takes 30 minutes or less to hook this up for all 8 units, and that provides makeup water to the steam generators. Not being satisfied with one, we have a second way of making up water to the steam generators, which can be done through each individual unit. That takes about 90 minutes to hook up to all 8 units. And the time frame we have here is about 6 hours or so to do this properly. Next thing we need to do is make sure that the heat transport stays full of water. Obviously, you know, in order for it to circulate and cool, it needs to be full. When you bring a reactor down from power and the heat transport fluid cools, it shrinks, and you have to add makeup water to keep it full. The 2 Bruce reactor designs actually have a very unique feature. It's not seen on many reactors. We have what we call the heat transport accumulators. They're large tanks with a large bunch of water stored in them, about 625,000 liters or so, which are pressurized by nitrogen, require no pumps. They're sitting on the system, and they will supply water to the reactor automatically when you need it, and there's more than ample supply there to keep the heat transport system full. There are 2 gate valves which need to open in each unit. Those are supplied from all the emergency powers on site, but we've also provided a hookup to the generators to actually, to the portable generators to also open these valves. They can also be opened manually as well. So there's multiple ways that we can make sure that we get the feed water in. The next layer of defense, should all that fail and you want to keep the fuel cool, is to keep the moderator full of water. The moderator is not a pressurized system. It has very large rupture discs on it. So you add water. We have a number of ways of adding water. The main thing we needed there was the pumpers, which we have, and we have our severe accident management procedures, which allow us to add water today. Unit 1 and 2 have also been hooked up with a quick disconnect type of system, and I'll show you what that looks like in a minute, and the other units will follow. And finally, shield tank makeup and protection. So the shield tank actually surrounds the moderator. It also includes the end shields. It's another set of cooling that we can use to prevent, should the fuel come out of the fuel channels, it prevents it from sinking down to the bottom of the vessel onto the floor. So shield tank makeup and protection. Makeup is again provided through the pumper trucks, through a kit that we've provided. And we're looking at overpressure protection there, and we'll talk about the schedule as I go further through this a little further. And last but not least, the two fuel bays are also supplied with makeup water. So just to give you a sense of what this looks like, this is the boiler steam relief valves. These are the manual stations that you can use to open those valves if you need to on manual, even though the station may in fact be in a blackout mode. Emergency supplies for power and water are shown here. On the right-hand side, you see the what we call dry hydrants, and I'll show you what those are. And the power supplies, one in each unit, one in unit 0, and one for the emergency filtered air discharge system that's on containment. So the source of water comes from the big pumpers that we have on site. We have 5 of them now. The dry hydrants are at the tip of that arrow. We can also, just below that, you see a dock at the outlet channel. We can also do it from there. So again, 2 redundant systems, 2 different places that we can pull the water from. So high capacity pumpers, 3,000 gallons per minute capability. Only requires one of them actually to feed all the boilers in a station. These are the dry hydrants I talked about. These actually just a pipe that drops down into the channel that flows out into the lake. This operates at lake level, so you're essentially drawing on the lake here. You hook them up to the suction side of the truck, quick and easy, and now you're ready to pump water out the other end. And this just shows you how the connection point works from the truck. Connect on there, and another quick connect in the station to the inner unit feed water tie, and you're now ready to supply water to all the boilers in either station. So that's the 30-minute hookup, that particular version. Here's a few pictures of some of the, now looking at the individual unit hookups. Remember I told you there are 2 ways. One I just showed you at the inner unit feed water tie. This is in the units, and so there's some pictures here of how that happens. Again, you see the quick connects that are here. You just hook up to them and you can supply water. Heat transport system, I talked about the accumulators. These big yellow tanks you see in the foreground here, that these 2 are the nitrogen tanks that actually drive the water. Just in the background, you can see the 4 other big yellow tanks that hold the water. And like I say, the 625,000 liters there ready to go. On the top left, you see the actual gate valves I talked about. You see the manual hand wheels there. They can be opened manually. They can be opened on backup power or on battery power, and they can be opened up on power from the portable generators. All this is actually in place and operable today. And this just shows you sort of a picture of how it works. This is the moderator makeup, quick disconnects over at Bruce A on units 1 and 2, and these will be added to the remaining 6 units as well. The moderator makeup and the heat transport makeup to the quick disconnects, that begins happening with unit outages in 2016. 3 of them in 2016, 3 in 2017, and the last 2 in 2018. That'll be the moderator and the heat transport makeup connections. Meanwhile, we do have the SAMG process that we can use to hook up manually. The quick connects are meant to be physically diverse, provide a second way of doing it that's different from the first way of doing it and provide a faster way. Although in truth, in the analysis, neither the moderator the moderator does not need to be done in a short period of time. You have time on the moderator system. And these are the fuel bays. So we have a primary fuel bay in each station and a secondary fuel bay. The secondary fuel bay on the left, you see the hookup there outside, and the primary fuel bay, the hookup on the inside. Again, the very same hookup, just a quick disconnect for the fire trucks to hook to.
Our program for the Fukushima event, really a simple concept. We're taking everyday pieces of emergency response equipment, such as fire trucks, and we've trained our staff to be able to deploy them in an unconventional method. So really, instead of fighting fire, we're making connections that are hard piping onto the stations themselves to provide cooling in a very timely fashion to be able to ensure that the reactor cores remain cool and the fuel bays remain covered with water.
Now to talk a little bit about emergency power. Again, all the philosophy here is with quick, simple connections with material and equipment that the staff are used to using. So the first thing we should point out is we have a fair amount of redundancy in backup power. We have 4 standby generators and 2 emergency power generators at each station. Although the emergency power generators are called qualified power supply at Bruce A. Different name, but same system.
We have existing standby generators and emergency power generators that are part of the plant design. There are also other backup power systems.
We have diesel generators that back up our class 3, and then we have other diesel generators that back up our qualified power supply. And we realized that if we lost all of our fuel tanks, we needed another backup.
They're in place to make sure that if we have a loss of class 4 power or other power losses, that power still gets to the critical parts of the plant.
So you see here a few of the tractors and other things in our storage building that we use for this equipment. So a few pictures to show you. This is the Bruce B side, the 100 kilowatt generator plus the hookup that this is one of the units. I'm not sure which one. I can't quite read the sign. These are all marked inside the station so you can't misread them, and the doors leading in from the outside are marked to lead the teams in the right door to do this so that they don't have to fumble around in an emergency doing it. Again, these are the 700 kilowatt generators. There's a redundant generator there. There's only 6 required, and we have an extra. This is them being deployed. I think this was actually here on Challenge. This is at Bruce A side. The electrical system Bruce A is a little different design, so we have a 400 kilowatt generator there, and this is it hooked up over at Bruce A. This is back at Bruce B with one of them again. The quick connects from the generator itself, pretty straightforward. And on the left here you see the Bruce A connection, and on the right you see the Bruce B connection. Say they're slightly different systems, so they had to have a slightly different hookup in them, but that was done on purpose. The other thing, of course, is this was a lot of new equipment and a lot of new operating skills that hadn't existed exactly before. So we needed to do the task analysis and develop the training and take people through the qualifications and invent some new qualifications to do that, and that's been done. We're still looking at the systematic approach to training on the broader ERO skills, the guys that are in the emergency management centers and the like, and there's still some work ongoing. But all the emergency response personnel have been through this and had this training and have done it many times now. And we haven't forgot about one of the key risks. I mean, there's some danger sometimes when you get looking at the exotic risks, the tornadoes and the big, that you forget about the sort of day-to-day things that are problematic. And the one that's probably the biggest risk for us, and I think it's probably the biggest risk for any building or any house, is actually fire. And so we haven't forgotten about that. We've been doing a lot of work on this as well, both because it's a risk day to day, and of course in a catastrophe when things go wrong and tornadoes go through, sometimes things catch fire. So we've done a fair amount of work in this regard. In fact, we were just this morning doing the grand opening on the fire training facility, and these are a couple of the pictures. This isn't really the plant that's burning here. These are mock-ups in the fire training facility. It's a 5-story building. As you can see, a nice big turbine generator set that people take quite joy in lighting the fire. This is a cable tray, a very standard thing in the plant. And here's a heat transport pump. So you get an idea. We have 11 what we call design basis fires in the plant, and they're all here, along with a number of external fires like vehicles and other things that we might have to fight, and as well as some pans that we can use to train on the foam as well. So having all the equipment is great, and making sure we know how to use it is great. We also need to know how to work together and coordinate the activity. Huron Challenge was a big exercise in that regard for us to test it out, and next year we will do another major exercise to work through this. I got a couple little clips here from Huron Challenge, I think, which...
This is the Drill Ops Chief.
Emergency Services is presently en route with the required equipment to B. They are clearing the route to A. They have all the resources they need at this time.
So clearing efforts underway to A still?
Correct.
And they're moving emergency support equipment from here
En route.
from 88 Farrell to GSB.
Correct.
The first challenge is a blocked road from tornado damage en route to Bruce A. Bruce Power first responders are being trained on payloaders and know how to remove debris. The payloader makes room for the fire trucks to get to the stations. The fire trucks can now pass through and get to the station to cool the fuel. Arriving at Bruce A, the team must attach hose from the dry hydrants to the trucks to pull water from the lake and pump it onto the fuel. These trucks can pull up to 3,000 gallons of water per minute, more than double the ability of standard fire trucks. They must then attach hoses to the fire trucks to deliver water to the stations. A tractor and hose trailer are used to lay hundreds of feet of hose to supply each station's 4 reactors with cool water. The water provided to each reactor keeps the fuel cool, and the risk for overheating is eliminated. Simultaneously, they must carry emergency backup generators by tractor. Bruce A has one 400 kilowatt generator and 6 100 kilowatt generators go to Bruce B. These generators run for 36 to 48 hours without having to refuel. While the team sets up the fire trucks and generators, those working inside the plant prepare to receive the cool water and power.
And of course, during Huron Challenge, the other side is what's going on out in the community and how you support that and make sure that the equipment is there. These are a few pictures: Canadian Red Cross, Health Canada copter doing radiation surveys over the site, the OPP doing rescue up in Port Elgin. Some students who were happy enough to pay casualty for us and test out the hospital facilities. They seem to enjoy this sort of thing. The Emergency Workers Center in the bottom right, which not only was set up in Kincardine, but actually moved to Port Elgin in the middle of the drill to test out its ability to do that. The field hospital here, which was set up in the parking lot of the Southampton Hospital as part of the drill, and one of the houses that was destroyed in Port Elgin as part of the overall scenario. And in truth, they actually destroyed this house. It was one that was being taken down, so it was a real demolition. So they mounted a considerable rescue in there to get people out of the house that was trapped in it. So it worked out, and it was fortunate that the developer was willing to let us use his prop in the exercise. And to do that, we had to set up a fairly large control area, and so we did that in our large auditorium on site, just to control all the, to send the messages out.
Also at the Bruce Power site, Exercise Control, or XCON, continued to set up challenges for the 71 participating organizations in the 4 counties of Grey, Bruce, Huron, and Wellington. XCON is made up of staff from each participating organization and Emergency Management Ontario. These small teams of people exemplify months of planning for each exercise theme. The teams at the various emergency operations centers react to situations called injects, provided to them by the XCON team. Huron Challenge was one of the largest emergency drills carried out in Ontario.
And of course, the last thing we needed to test was the durability of the trucks and the pumpers themselves, so we put them through a 24-hour run.
Back at Bruce B, the fire trucks continue to pump water well into the night. The trucks have refueled and must continue to pump water for 24 hours to prove they are self-sufficient. Having proven self-sufficiency for over 24 hours, the following morning, the fire trucks are allowed to be shut off.
Site 1, this is Bruce B. Pumpers. Confirmed successful refueling through the night. Trucks have ran successful for 24 hours. Request we shut down, over.
And in fact, we used our portable pumper to fuel those trucks while they're operating. You have to fuel them about every 5 hours when they're running full tilt like that. So the portable truck comes around, fills them up while they're running without interruption. And of course, the next step is, what about off-site? Should the emergency get to the point where there's an off-site release, how do you deal with that? We've developed a new off-site monitoring system out to 10 kilometers, which will automatically detect any radiation released. And in fact, it'll operate 24/7 whether there's a vent on or not. But this will provide very accurate and detailed tracking of any radiation that might be released in an emergency, thereby allowing the government to easily move people out of the way.
The remote monitoring system at Bruce Power consists of 44 spectrometers or radiation detectors. The system itself is fully redundant in the sense that the detectors themselves are battery operated, and they have trickle backup solar panel charge to sustain operation. The data from the detectors themselves are sent through the cellular network that provides us the capability to have near real-time remote monitoring around the Bruce Power site. Where we retrieve the data from the detectors is within our emergency management center, and the emergency management center itself is also fully redundant in terms of backup power and backup communication systems. So as you see behind me, we have a remote monitor. Very sensitive detectors. In fact, they're so sensitive they'll actually pick up on everyday common household items. In terms of expanding our public notification system, we've looked at not only use of sirens, but also capabilities such as FM radio connection to the public alerting system within the province of Ontario.
You can have different normal or high priority messages, and I'll just type in, this is a test, so I'll hit send now, and that is sent.
More recently, we've worked to expand that system where we've worked with local cellular carrier to do an SMS text demonstration, location-based cellular public alerting, which was very successful. So we're looking at furthering that effort, not only working with that cellular carrier, but also a number of other cellular carriers, so that whoever is in the area, regardless of what carrier they're with, they'll be able to receive any public alert message through their cell phone. The whole idea here is enhancing public safety, and we're constantly evolving our program to make it the best that it can be.
So just to summarize and go through, what's in place and what yet has to be done. So fast hook up to the lake water, alternate hook up to the lake water supply, fast hook feed water to individual and unit boilers, the inter-unit feed water tie, and manual opening on the boiler steam and relief valves on all units. Fast hookup water connections to the primary fuel bay and to the secondary fuel bays. Fast hookup water connections to the moderator on Unit 1-2. Heat transport makeup from ECI accumulators and passive autolytic hydrogen recombiners, all done and in place. Sewer accident management method to make up water to the heat transport system, and the sewer accident management method to make up water to the moderator. This basically means that we manually hook it up rather than using a quick disconnect to do it. Fast hook up electrical connections for each unit and the common systems, and well as the EFEDs. Fast hook up electrical connections for containing emergency filtered air discharge system. Again, all in place. Support facilities, a new emergency management center in place, portable command post in place, communications capability independent of local end structure, so we don't require wires or even cell towers to work. New fire training facility, as you have just seen. Portable high capacity water pumpers, 5 of those. 12 portable power generators, portable fuel retrieval and delivery truck, portable equipment transportation capability, again, all in place. Heavy-duty equipment for route clearing, portable equipment storage building, firefighting equipment, and a maintenance and testing program for all that equipment, all in place as of today. Off-site support in place. We've got a communication system that works very well. Can talk to people virtually anytime. The radiation monitors out to 10 kilometers are in place, and we have deployable radiation monitors that we can deploy beyond that should we need to. Potassium iodide tablets, we actually just started to get the delivery today. They were a little slow, so this is them in the new package, and we can let you have a look at those after a bit if you like. And this is a booklet. It's also on the Be Prepared here on Bruce Gray website now with all the different emergencies in it, including nuclear. The FM alert, the radios are here, the system is ready to go. We opted to do the distribution after we do the KI pills so as not to confuse people, so we'll be doing that very shortly. And that'll actually be a fairly broad distribution because we don't see the FM alert as particularly a nuclear capability. It's a capability that the communities can use for emergencies in general. It just includes nuclear. Safety assessments. Our chief engineer is going to talk here in a minute about the safety assessments and where we've got to, but we've included some pretty extreme external events in here. Despite that we broadened the events and broadened the requirements considerably, the addition of the EME, as you might expect, the emergency mitigating equipment as a whole new layer of defense, has made a significant improvement on the overall outcome of those PSA results. And we do have a new capability we're working on to actually assess the deployment success in the world using Monte Carlo methods. And we have the basic model in place, and we're actually trying to prove it and validate it this year. So here's a work in progress, fast hookup moderator to the moderator and to the heat transport system. As I said, those are outages starting in 16, so 3 units in 16, 3 in 17, and the last 2 in 18 to put those in place. They have to be done during unit outages, so they have to stagger through as we go through. Connection points for additional filtered air discharge. We start the Bruce B vacuum building outage on Wednesday, and the first one for Bruce B, they'll be added at that outage, and Bruce A will be added next year during their outage. Shield tank overpressure protection, that's in the final design stages, and we'll have a plan in place exactly when we're going to do that by the end of the year. It'll likely be in the same time frame as the moderator makeup. The makeup water kit is already available through the, or will be available this year for the shield tank overprotection. We feel that we've taken the Fukushima events very seriously, applied the lessons actually in a much broader sense than they would have applied in Fukushima, looking at not just those kind of events, but just any kind of event that might occur. We think our crews are well trained, they're on standby 24/7. So we feel that we have the capability in place to deal with virtually any emergency that will come our way. We certainly invite you to drop by our visitor center and have a closer look at the plant and the site and the facilities here. And I think you too will walk away with a level of confidence that the place is well looked after and we're well prepared. That was a little long, but I thought it important given the central place that Fukushima has taken in the last few years and the amount of effort and time into it to really go through it in some detail and talk about what's really in place, fully in place, and what's yet to be done. So that's it for that presentation. I'll now move over to Mr. Newman here to talk about PSA.
Okay, excuse me. Thank you, Frank. Good evening. For the record, Gary Newman. I'm going to be speaking to you this evening about assessing and understanding risk. We'll be doing so at a fairly high level. Obviously, we could spend a number of days discussing this topic were time available. So for the purpose of this Part 2 Commission hearing, we felt it was important to provide more detail on all the work completed to evaluate both internal and external sources of risk, which in turn demonstrates that Bruce Power is compliant with current CNSC regulations. So as mentioned, at a high level, I plan to speak to the following aspects: the historic perspective based upon relevant regulation, which will include establishing and sustaining a credible design. It also involves improving the design through risk-informed enhancements. We'll then move on to discussion of the evolution and updates to our safety assessments. That'll be followed by a brief discussion on new tools, and Mr. Saunders has already touched on some of that. The ongoing plant and response planning enhancements, again, already touched on by Mr. Saunders, and then a brief summary. So beginning at the beginning, which is really the Nuclear Safety and Control Act, the Act speaks to a reasonable level of risk, which is consistent with the value proposition associated with the safe, reliable, clean, and low-cost energy production through the use of nuclear technology. This, of course, has an explicit commitment to meeting both our domestic and international obligations, just like all responsible operators of such technology around the world. The term reasonable, of course, will always be the subject of debate, but in general, we have considered industry events that are less than 10 to the minus 6 as incredible. So achieving a reasonable level of risk is a multi-tiered undertaking. However, first and foremost, it begins with an acceptably safe design. For new plants, this guidance is captured in CNSC Regulatory Document 2.5.2, and for existing plants, Bruce Power has adopted the International 75-INSAG-3 Rev 1. To this end, I should note that the large release frequency criteria captured in that document are less than 10 to the minus 6 for new plants and less than 10 to the minus 5 for existing plants. And of course, once operation begins, one now needs to sustain the safe and reliable design, and this is accomplished through a combination of the following: monitoring and testing to demonstrate continued operability and reliability of important systems in accordance with that design. In addition, we evaluate and implement important design changes against the design goals. We also periodically evaluate against new standards to test ourselves and assess the opportunities for improvement. This is part of our ongoing continuous improvement philosophy at Bruce Power. The design requirements were established in the original siting guide, which identified the deterministic design and operating requirements and sets the single and dual failure dose limits. From a safety report viewpoint, probabilistic assessments were added to the original deterministic tool set beginning in the 1990s. At that time, goals and limits were set for severe core damage, large and severe release, as well as public health criteria. These early PSAs embraced release thresholds that were approximately 5 times larger than the current values, which has resulted in the need to produce more accurate predictions within the current assessments. These historic PSA assessments were completed after the plants were in operation for many years, rather than as part of the design activity. Modeling activities were focused on comparing with the new expectations, so in general only enough work was completed to confirm that the limit was achieved. This meant that many supporting systems were not modeled but simply assumed to not be available as a result of the event, and which adds a considerable amount of conservatism. These assessments were focused on internal plant events, including the loss of off-site power, the latter of which was a single external event that was considered. As part of the safety assessment evolution, a greater focus on external events was established by CNSC Standard 294 in 2005. However, post-Fukushima, it was decided to broaden the approach to consider lower probability external events, accommodation of a larger consequence but lower likelihood event, and lastly, equipment diversity in the context of the robust nature to resist external disaster scenarios. As per normal practice, updated regulatory documents in terms of both deterministic and probabilistic assessments were issued to guide this work by our regulator. The release categories were first updated in S294 based upon international practices and again documented in the regulatory documents when these new documents were issued. So in the case of new reactor facilities, the sum of the frequencies are considered as follows. In the case of severe core damage frequency, the sum of the frequencies of all event sequences that can lead to significant core degradation shall be less than 10 to the minus 5 events per reactor year. Similarly, small release frequency is the sum of frequencies of all event frequencies that can lead to a release to the environment of more than 10 to the 15th becquerels of iodine-131 and are required to be less than 10 to the minus 5 events per reactor year. And in the case of a greater release, may require temporary relocation of local population. And finally, the last release related to large release frequency is the sum of frequencies of all events that can lead to a release to the environment of more than 10 to the 14th becquerels of cesium-137 and are required to be less than 10 to the minus 5 events per reactor year. And a greater release may require long-term relocation of the local population. These definitions were developed based on internal plant events, and there remains a discussion about how to properly integrate external and internal events and properly calculate an accurate aggregated release frequency. However, for the purposes of today's discussion, we have simply added them, although we know this is a conservative treatment. As an example of the continuous improvement process, work has been completed to enhance the Bruce A and B safety reports through updated PSAs, which consider fire, seismic, high winds, and flooding under both operating and shutdown conditions. This was completed against the backdrop of updated PSA release categories. The following lists the safety improvements that have been installed in the plants and were included in the internal plant event assessments. So for example, the emergency makeup water from portable equipment directly into the boilers as already described by Mr. Saunders. I do not plan to go through the list. However, most of these improvements have been fully installed and credited within the PSAs. Fast makeup water to the heat transport system is currently insured by additional emergency power to the emergency coolant injection accumulator tanks. Another committed makeup path for emergency mitigation equipment utilizes severe accident management instructions can also be established. Installation of a third path through quick connect fittings is in progress. Makeup water to the moderator system from emergency mitigation equipment utilizing severe accident management instructions can also be established. Installation of another path through quick connect fittings is in place for units 1 and 2 and in progress for units 3 to 8 as already described. I should note there was one additional bullet that may not be on your slide, and there's a makeup water to the heat transport and moderator systems, which we added afterwards. As a numerical demonstration of the benefit achieved for the example of at-power events on the large release frequency, this table shows from top to bottom the current results with EME credited versus earlier calculated values, and the final row with no credit for EME for each of the stations. One can see the drop from 10 to the minus 6 range into the 10 to the minus 7 range when one credits emergency mitigation equipment within the PSAs. Also, the estimated values for EME were provided in the July submission to the CNSC and more precisely calculated in the November license application update. The estimates proved to be pretty accurate. Some safety improvements that were committed and currently in progress, as already described by Mr. Saunders, are credited in the station aggregation for large release frequencies. And external events, for example, enhancements to containment robustness for multi-unit events. Although still a very conservative calculation, it demonstrates the progress that has been made through the Fukushima enhancements and the value of the work still in progress. It is also important to note that site aggregation of single unit event frequencies did not attempt to remove the inherent redundancies, and results are considered to be conservative. And lastly, industry-driven further work is underway to develop a site-based risk model, which we believe is currently leading the industry in this area of development. So on the next slide, we have results for the severe core damage. This table provides those results for each station, for the combination of internal and external events, for single unit aggregation results in column 2, as well as station aggregate results in column 3. All of these results meet the requirements of the current criteria. On the next slide, we similarly summarize for large release frequency. These results demonstrate that on both a unit and station basis, we meet the current acceptance criteria. Just like I described for the severe core damage frequency calculations, we have similarly credited installed EME for release category assessments, and you can see examples of the noted improvements in the following table. So for example, the design basis events at both stations, one can see the frequency improvement when crediting EME. So that would be comparing the third and the fourth columns. These release frequencies, while still very unlikely, are the most probable. The releases would occur as a result of venting of containment through the emergency filtered ventilation system. This type of venting maintains containment pressure low and prevents release of isotopes that can result in longer-term contamination. These are the type of events where shelter in place may be a viable option, and as Mr. Saunders has indicated, the use of potassium iodide may be directed. Similar for the example of large release frequency for Bruce A for the various categories, the decrease in frequency when EME is credited. So this again would be columns 3 versus 4. Release category 2 is approximately equivalent to the generic large release defined in the CNSC study of consequences of a hypothetical severe accident and effectiveness of mitigation measures, which examined the extent to which contamination might spread and the potential dose to people. As you can see, the probability of this event is less than 10 to the minus 6 cutoff, normally associated with the credible versus incredible event. And on the next slide, the same again for Bruce B. Decrease in frequency when EME is credited, well below the 10 to the minus 6 cutoff, normally associated with incredible events. And on the next slide, and in the case of small release frequency reductions for Bruce A, when EME is credited, similar sort of improvements are observed. I should point out that the term small release by definition includes both small and large releases and might more accurately be called all releases or total releases, but this is the current accepted terminology. And on the next slide again, the same outcome for Bruce B. And again, as I already noted, the term small release by definition includes both small and large releases, and might more accurately be called all releases or total releases. Moving on to some of the new tools that we're deploying, and again, this was touched on by Mr. Saunders. developing which enhance emergency response capability to aid in our already extensive drill requirements by simulating events to identify areas for improvement within existing practices to make them even more robust. The tool also provides, through Monte Carlo simulation, the probability of successful deployment of EME under a wide variety of circumstances and points out potential challenges which can then be adjusted to further enhance our response capability. As I noted earlier in the presentation, there are a number of in-flight projects that are being implemented to add further enhancements to the stations. And these are all on track as described by Mr. Saunders as per schedule and as communicated through formal correspondence with the CNSC. Current ongoing work supporting response planning, including, as already mentioned, 44 installed monitors within a 10-kilometer zone, automated real-time plume tracking system supported by portable monitors available for additional deployment with implementation of automatic real-time feed to both the province and the CNSC organizations. It is important to note that this is not just a paper exercise, but that the information gained from these assessments is being utilized to enhance both on and off-site emergency response capability. In addition, work is underway to develop enhanced predictive plume modeling at the industry, provincial, and regulatory levels. And this modeling capability will support assessment of a suite of accident scenarios. This is consistent with the practice by the US NRC. Working with the province and the municipalities to improve public alerting capabilities for all emergencies through the use of such technologies as described already as the FM alert, which provides further defense in depth, and this is due to begin this spring. In addition, we are working with Pelmerex and communication companies, as already described in the video, to establish a cellular text alert system. Again, and as already noted, we are building additional barriers to ensure continuous improvements to our response capability. An additional element of our response planning is the distribution of potassium iodine, again, as already discussed, to a radius of approximately 10 kilometers. This measure is just underway with the necessary instructions along with website and public information sessions. Once this is complete, we will have measures in place to sustain the program through a periodic refresher program. And lastly, distribution centers will be set from 10 to 50 kilometers to allow those access. So then in summary, we have stated before, and I wanted to reemphasize, that Bruce Power and the industry have been diligent over the operating life of our plants to review plant design against modern standards, including safety assessment methodologies, and to actually apply this knowledge in real plant enhancements. And I think we've seen some of those in the prior presentation tonight. The continuous improvement in plant performance that has resulted from this effort is a demonstration of the superior approach in the Canadian regulatory environment, which encourages ongoing improvements. The Fukushima enhancements have been effective at reducing overall risk. Based on the current practice of analyzing large release frequency against in-plant, and this includes multi-unit events, Bruce Power not only meets the international standards for releases for existing plants, but for the most part would meet the requirements for new plants. The work already committed for Bruce A is expected to also bring Bruce A in line with these numbers. We do expect, as aggregation of individual results is considered both in Canada and internationally, changes will occur in some of these methodologies. Bruce Power will continue to participate and support this effort. We have considered the release category results of the PSA work as well as the CNSC study on hypothetical severe nuclear accident and effectiveness of mitigation measures in relation to off-site emergency planning and find that the current planning zones are adequate, but that the reliance on local infrastructure for monitoring and communication in a regional disaster scenario need to be reduced. Finally, it should be noted that the calculations to complete these assessments were rigorous, with the final results encompassing nearly 40,000 pages. Large amounts of time could be spent debating all the possible perturbations, but the work was completed in accordance with approved methodology and at a high level has been summarized in the preceding series of slides. Thank you.
So Frank Saunders again for the record. One short presentation left from our side anyway. And this really goes to some questions we had from the commissioners at the last part one hearing around what were the sort of monitoring points we used to assess public dose. So this is just a short presentation to show you where those various monitoring points are and what they look like. So this is our environmental policy and the key points that we use in our day-to-day operations. Environmental management encompasses a number of programs. There's an ISO 14001 which governs our management system, and then CSA standards govern how we actually carry out a number of these activities. This is just a depiction of the way that we would assess the dose. You see a family here in the center, somewhat right of that picture, and the various ways that emissions from the plant or from anywhere else could actually make their way to them. And this is how we actually assess what the dose might be from the food you eat, the water you drink, the air you breathe, and so forth. So our normal dose that we found in terms of the members of the public, and it's been pretty consistent ever since we became Bruce Power, is in the order of 0.1% of the safe allowable limit. So this is where we sit, you know, in the province of Ontario. The two sources here, of course, the Bruce B on the bottom and Bruce A on the right, a blue and a red figure there just indicating air and water emissions. And this picture just shows you the air monitoring stations that we have scattered around. That takes a continuous air monitor, a continuous air sample, and monitors it, picks it on a filter, and allows us to go back and look at it later. This is a picture of one of those stations. So here are a number of the farm sites that we use to sample, and of course we're sampling pretty much what you expect, anything that's grown or eaten or produced on the farm. We ask for people to voluntarily participate, and many of them do, and they supply us with these materials so we can check them. So this is these are a number of residents where people live, sampling sites. So we do things like sample the water, flowers, vegetables if people are growing them handy, and we use this as part of our input into the dose calculations. You can see there's a fair number of sites that we use. Again, this is all voluntary on people's part, not something that we control, but we ask for volunteers, and people have been very good about it. These are the creek sampling sites, or streams if you'd rather call them that. So there are a number of streams around the site that we also sample to look for any kind of runoff or water. These are thermistors. This is the way we monitor temperature in the lake. We do have a challenge keeping these thermistors in the lake when we go through the transition when we just went through from winter to the spring. We have a tendency to lose them all, and then we start all over again in the spring. The ice here gets quite heavy, as you can imagine, and tends to kill them. But they're kind of a neat little contraption. We've actually had some studies underway to turn this into a much like the off-site monitors, into a radio beacon that will send the signal up, and we can get it real time. Right now they're recorders, so we're working on that. We had a test one that worked okay. We just need to look at how to do a production now. It has to be reasonably cost, because, like I say, we go through a fair number of them. And this kind of puts it all together for you, just to show you the number of points that we look at as part of our dose. Water treatment plants, of course, we do look at Southampton and the Kincardine water treatment plants and measure the water intake there. These are all the wells that exist around the site. Some of them are deep wells, some of them are shallow, and some of them are industrial, and some of them are residential. We don't sample them all. We sample the number, and we keep a log of them so that if we should ever have an event or a release that we needed to warn people about, we know where the wells are. And on site, the one last question that we had was around well number 4 at Bruce A and Bruce B, because they were flowing slightly higher levels of tritium. And you can see in this picture here, the BB4 and the BA4 is that well. It's a multi-level well. And what that means is it's basically just a dry well. It's not actually used for anything. It's a sample well. And you can sample that at various different elevations up through. And so, you know, when you see sample says BA4 1, -1, -2, -3, it's just different levels in the well that's sampled. And they're on the lake side because we're looking to see whether there's any transmission moving from the plant towards the lake. And they're there to tell us what goes on. And that concludes the presentations. Thank you.
In summary, members of the Commission, I think we tried our best here to provide explanatory information on some of the points that were of interest at the day one hearings. And as I mentioned earlier, the intention here was to provide a bit more explanation of some of the points that either Commission members raised or we felt were appropriate given the tone and nature of some of the interventions. So, as was mentioned, we're available to answer questions, but the Commissioner have chosen to do that tomorrow, and that's fine. But I just wanted to say, just in conclusion from Bruce Power, that I myself can't be here all days of the hearing, but I'm certainly available if the Commission have any specific questions to ask of me over the course of the next 3 or 4 days. But I can assure the Commission that senior officers of Bruce Power will be here throughout. Thank you very much.
Thank you.